of this group, and I regret that I could not come earlier. I had 2 final exams yesterday. I really had to be there. The topic of my talk, as you see, is dynamic Eshelby micromechanics, which I will explain to you what it means. Eshelby mechanics mean 2 things. These are 2 of the famous Eshelby papers: the force on an elastic singularity, that is configurational forces, driving forces, the conserved JLM integrals, that is the subject of this symposium here, and the ellipsoidal inclusion in 1957, which is that the ellipsoidal inclusion has the Eshelby property, which is that the stress, constrained, strained, and stress inside the ellipsoid is constant. And this property has allowed to solve the problem of an ellipsoidal inhomogeneity under remote loading or transformation strain loading by the equivalent inclusion method, that is considering that you have one material and in the place of the inhomogeneity you have equivalent eigenstrain that you can find analytically because of the constant stretch property of the Eshelby inclusion. Eshelby tensor is the tensor that relates the constraint strain to the transformation strain. So this is just the basic result. Now, we have the result that for self-similarly expanding ellipsoidal inclusions, the constant stress property inside the ellipsoid is also valid. This is due to the fact that the hyperbolic system of partial differential equations reduces to an elliptic system for subsonic self-similar motion. And this, I will show you the proof briefly, shows to the result that for self-similar expanding ellipsoids, the constant stress property is preserved. And so we have obtained for the self-similarly expanding ellipsoids also the dynamic Eshelby tensor. This dynamic Eshelby tensor then allows us to solve the expanding inhomogeneities. So that is an expanding inhomogeneity of different material, let's say with transformation strain. So as it expands, the material changes because the new region now will be of the material of the inhomogeneity. And so we can solve this problem analytically. We have also obtained the driving force, that is the energy release rate for self-similarly expanding sphere. Now, for the first part of the force on an elastic singularity, we have obtained the driving forces with inertia effect due to an expanding inclusion with transformation strain. So we have solved the problem of a spherical Eshelby inclusion that I will show you in with general transformation strain, and we have obtained the plane boundary as the limit of the sphere as the radius of the sphere goes to infinity, and it becomes a constrained plane inclusion. And so the dynamic L integrals allow us to obtain an equation of motion for the moving plane boundary for general motion. Equation of motion means when you include in the loading the external applied loading and you have all the interaction energies. So we come now also to asymptotic homogenization, which is that if you have periodic distribution of unit cells that contain, let's say, expanding inclusions, can be also moving dislocations, then in the microscale, in the unit cell, the evolution of the defects will be according to Eshelby mechanics. And analytically, by asymptotic homogenization, this can be brought as damage in the macro scale. I'm going to show you examples of that. And having now these fundamental solutions of the self-similar expanding inclusions that preserve the Eshelby property in dynamics, we can also do the evolution of damage by asymptotic homogenization, and that is important. The self-similar solutions are important because they grasp the early dynamic response of the system. Sorry. So asymptotic homogenization, briefly, I love this method. Many deep mathematicians have worked on it, Lyons and Papanikolaou and the Russians. And so essentially what you do is you renormalize the unit cell, you blow it up by a lens, you solve the problem exactly in the unit cell. In our sense, we don't solve it exactly, but we solve it to the leading order in the singularity. And this effect of the leading order in the singularity, we carry it analytically to the macroscopic scale. So, for instance, in this problem of two interacting cracks, we have the solution for the unit cell. Then what is the singularity of the interacting cracks? That's the Sadovsky solution. And then, we homogenize with the machinery of the asymptotic homogenization. If I have time, I will show a few things. And then we obtain the acceleration of the damage in terms of this singularity of the interacting cracks to the leading order. Now, we also have some recent work on damage amplification due to interacting nearby cavities. Now, the interacting cavities will grow when the value of the M integral, which is for self-similar growth, reaches a critical value. And we have the two examples that we have small holes near large holes, and two loadings under remote tension or under internal pressure, and the singularity is different in the two cases. So we will see how the damage will be accelerated more for the pressurized cavities. So this is in brief to outline. So macroscopic energy dissipation. So we will extend now the asymptotic homogenization to dynamic asymptotic homogenization, which is only for the early times of the system, so the waves don't have time to go to be reflected from the boundaries and come back. With this is easy. This follows past work of mine with Rod Clifton at Brown, who was a plastic waves person and experimentalist, that the elastic precursor decay, that is the decay of a plastic wave, was explained from the energy due to dislocations being set in motion by the incident wave, and the energy computed for the dislocation to be set in motion was, of course, by the dynamic J integral, the energy release rate due to its dislocation. And Eshelby confirmed this approach with his experimental results. So, in essence, we can continue this for expanding inclusions. I will briefly go over some of these results. Here we have a spherical inclusion, and the radius of it is expanding in general motion, L of t. The solution is given in terms of the dynamics Green's function in an infinite solid. Willis gave the formula, but Willis did not have the boundary to expand, had only the eigenstrain to be time dependent. Here we have the boundary to expand. you obtain the solution. Of course, it satisfies the Hadamard jump conditions at the interface. So this is a fundamental solution, and now we want to obtain the plane boundary, not the spherical inclusion. So the question is, what does it mean, plane boundary? I was talking to Dick James at that time in 2010, and he said there are not unique solutions. So let's see. Let's consider an Eshelby inclusion. Here, the Eshelby inclusion is a unique minimum energy solution in an infinite solid. And let's consider that the radius of the inclusion goes to infinity, so the inclusion is going to become a half space inclusion. So we take the solution, and so you are going to have then inside, in the interior domain, the Eshelby stress field. Outside, on the other side, from the Hill jump conditions you obtain the outside. So a picture like that means you have to apply on the boundaries tension or compression in order to have the half plane solution. This half plane inclusion is the minimum energy solution and is unique. If you want to compute driving forces for this boundary, then you use it for this solution. You can superpose tractions at infinity that are in equilibrium and keep the interface compatible, but they will increase the total energy of the system. So John Ganders, my collaborator, now 91, still very lucid, called them ROG states. So we did the same for dynamics. So we took the solution for the expanding inclusion, and we took the limit as the radius, the limit of the radius to go to infinity, and the inclusion to become a plane boundary, plane moving boundary. So then we have the plane moving boundary in general motion. And of course here you have to apply tractions, which is the limit of this solution that we have for the read. So the driving force you can compute for the plane boundary for this solution. Now I will not say much here, because we want to obtain the equation of motion of the unit boundary. The Nether's theorem is already was talked before in this symposium, so I will not go over. Now, let me make a remark. So, for dynamic J integrals, if we apply the variation of the Lagrangian functional, and according to the machinery of Nether's theorem, and epsilon is the infinitesimal translation here, there, you will get it in this form. These first two terms, this is called pseudo-momentum, altogether, this is the energy momentum tensor, this is what you would call dynamic J integral, and this term are the Euler-Lagrange equations, which are zero for conservation of linear momentum. So you can make the statement that if linear momentum is conserved, then the variation of the Lagrangian is equal to the dynamic J integral during an infinitesimal transformation of the defect. But you can also make the converse statement that if the variation of the Lagrangian is equal to the dynamic J integral, then if ij, k is invertible, the linear momentum will be preserved in the domain. So this is an if and only condition, and there is no issue about do you like to use the J integral or not. You have to. And moreover, we prove, this is in Rogers' journal in 2012, and we also show that the variation of the Lagrangian is equal to the variation of the Hamiltonian for translation of the defect. So essentially then, with this to be the variation of the Hamiltonian, as these J integrals L integrals, M integrals are dissipative mechanisms. As Eshelby says in 51, energy is lost, and the mechanics, it doesn't say where it goes. It can go to kinetic energy, it can go to any other energy. Look at energy 51. So this energy is lost during the change of the configuration. And so that's what we are going to do with the unit cell and the asymptotic homogenization. In the unit cell, this is a dissipative mechanism that happens by the J integral, and for the growth of whole by the M integral. This energy we calculate, and this energy is lost. Now, what is the equation of motion for an inclusion boundary? So with inertia, I think nobody else has inertia for these problems. So actually, the dynamic J integral is valid both for linear elasticity and non-linear elasticity. The advantage of linear elasticity is that you superpose the stresses. So if you superpose the stresses, then you can separate them, and in this expression here, this came from calculating the previous solution that I had, this solution with all these terms and this expanding sphere, and in the limit when it becomes a plane boundary, and there is also applied loading in the total energy, and you have interaction terms, maybe altogether a couple of dozen terms, and I was doing this, and all the terms were cancelling out miraculously, and there remains the term of the applied stress times the eigenstrain, which you can see that is like for dislocation, the Berger's vector times the applied stress, that is the Pitch-Keller force, and then this is the self-force altogether for the applied boundary, and the first term that we obtain by the dynamic Green's function, nothing is put by hand. This term is the same as Eshelby obtained for an inclusion, static inclusion of any shape, and Gavazza as well in 57. So we obtain it here, and then the term that depends only on the velocity, not the acceleration. For that matter, we say that the plane boundary doesn't have effective mass. So of course, the right-hand side is zero only for a purely mechanical system. There may be dissipation, and that dissipation may be the most important term and difficult term to evaluate, and many people are evaluating this term, but this gives the relation between the applied loading and the motion of the defect. So you apply the loading, you have to surpass the self-force, the static one, and then as you increase the load, you will increase the velocity, because this term is constant for subsonic motion. So you will need increase in applied stress to increase the velocity. Now, so I'm shown here that for dislocations this is equivalent. This is the paper of Eshelby with this title in Physical Review, and for the dislocation, the Pitch-Keller force balances the self-force of the dislocation, which now depends on the acceleration of the dislocation, and we have calculated actually the terms F and G that Eshelby has left undetermined. So these are the equations of motion that come out of the dynamic J integral. Now, I will show you briefly the proof that the self-similarly expanding and ellipsoidal inclusion preserves the Eshelby property. So we are going to have So these are the Navier equations of elasticity, and we have a body force term, and the body force term now is eigenstrain that is inside an inclusion that is ellipsoidal, that is self-similarly expanding. So S is a parameter. If it is a sphere, then that S would be 1 over V, a velocity of the expanding sphere. So we are going to have then the Navier operator to have this term K and this right-hand side. We follow, there is a technique, Verich and Willis have solved a problem, two-dimensional, for elliptical expanding cracks, self-similar expanding cracks. So our method follows, but with major adjustments. That proof is quite involved. I have presented at other meetings, but essentially you have to apply an M operator, and so that you can reduce the right hand side to delta function, and then the solution will give for the strain inside, the solution is going to be given in terms of integrals over the slowness surface of the Navier operator, that is the longitudinal wave and the shear wave speed, and the slowness surface of the M operator. The slowness surface of the M operator would be a sphere of radius 1 over V if you have a sphere that is self-similar expanding with V. So this would be these three surfaces. And you have here, we have calculated all these contributions of the poles of these surfaces that give the contribution to this solution. And we see that if you have interior points, this term will be 1, and this is 1, and that term will be 0. So for interior points, this expression is independent of x, because wherever is x, you have either 1 or 0. But for exterior points, then only part of the slowness surface of the expanding sphere contributes to the point. Then we have contributions from all the points. So the interior dynamic SLP tensor is given here, where A, B are the wave speeds, longitudinal and shear, and V the inclusion velocity. We have the exterior, there are 36 components. We have the driving force, and actually we have solved the problem also by stretching coordinates for self-similarity, and the solution agrees. Yes, that's fine. And the solution agrees, and actually the driving force here also, this term, if the radius is 0, as it starts moving, the driving force is not 0, but is the static driving force for the SLB inclusion, which is independent of the shape of the inclusion. It still is there for 0 radius. And so this is the driving force per unit area. And now I come to the singular amplification between holes and ligaments. We have the mingling problem, and if you have a free surface and a hole in tension, and the stress here has a square root singularity, so it will be infinite as 1 over square root of V. You have the Coiter problem, and here it will be as 1 over d over r. So you need to solve these problems by singular asymptotics or matched inner and outer expansions. But the difference, if these singularities make a difference, because if the ligament is 10 to the minus 6, Here the amplification of the stress is 10 to the minus 3, the tension at infinity. Here 10 to the plus t, the tension at infinity. If you have a pressurized hole, actually the infinite stress will be here on this boundary is 1 over d, is bigger than tension at infinity. So when you have two populations of cavities, so this is the Coiter problem. This is the Mindlin problem, because the large hole is like a half space. So, and when a small hole has coalesced with a big hole, the stress in the ligament is 10 to the plus d square, 10 to the plus 12 times the tension at infinity. You cannot do this by any numerics, but it means that this ligament will collapse instantaneously, and the small holes facilitate the large holes to collapse into bigger holes, or two small cracks to collapse into bigger cracks. So these asymptotics show you, the order of the amplification. So we apply these singularities that we have obtained to the interaction of cavities, and by asymptotic homogenization. So asymptotic homogenization will work like that. You have the small variable, you have to integrate in the unit cell, so you obtain the asymptotic homogenized coefficient as a function of the geometric parameter, that is, because you solve the problem in terms of this geometric parameter, function, let's say, of crack length d and ligament thickness. Then, so when we have the cavities here, in the unit cell we have a small cavity and a large cavity. On both cavities, the driving forces times the variation, the delta r of the radius, which we assume that is self-similar, RL dot, balances the rate of change of the total potential energy. But this difference, so if you have an inclusion boundary, it will be that the difference of the m integrals, the jump in the m integrals, L dot, will be the change of the potential energy. We calculate the change of the potential energy. So the change of the potential energy will depend on how the ligaments get closer. So dp dt is dp d delta dt. D delta dt comes into how the homogenized coefficient that we have calculated changes with delta, and we have this expression analytically. So from here you get that this expression is the energy release rate for the growth of hole for damage. These are the macroscopic strains at that position, function of position. This is the variation of the homogenized coefficient with delta, according to the holes, the previous solutions. We have them analytically. R over epsilon is the radius of the hole over the unit cell. This is independent of a constant in asymptotic homogenization. If you continue, the ratio of this over the side continues the same. So when this value of the damage reaches a critical value of the m integral, the holes will grow, and this is the evolution of the process. So this same evolution of the process, we can do it also for dynamics, because we have the dynamically expanding, so self-similar solutions and self-similar inhomogeneities. And we can do dynamic homogenization and use the dynamic M integrals to obtain the dissipation of energy for expanding inclusions in the unit cell. Well, this is a huge subject, so I try only to say just the very tip of it. Okay, thank you so much. I took that. Take it away.
What is your question here?
Yes.
It's fine.
Take this.
close the presentation.
Cavities, so another inclusions, and then to obtain
This is
You already did it.
for any general, for any transient phenomenon. It's not like a lot of people that include,